So hi guys, welcome back to my channel. In this video, I'll be basically going through a dataset which is going to try and identify whether a patient has or doesn't have the neurodegenerative disease known as Parkinson's disease. First of all, I'd like to give a brief overview of what Parkinson's disease is. Parkinson's disease, or simply known as Parkinson's, is a chronic degenerative disorder of the CNS or central nervous system affecting both the motor system and the non-motor systems. The symptoms usually emerge slowly over time and the disease worsens. Now, most of the symptoms associated to Parkinson's disease tends to affect the movement, okay? You get bradykinesia, you get a tremor, all right? And one of also the main symptoms of Parkinson's disease is dysarthria, therefore difficulty in talking, in speech production, and also progressing towards dysphagia. So dysphagia resulting in problems with swallowing and with eating. Because one of the hallmarks of Parkinson's disease can be speaking and talking, in this data set we're going to look at whether the recorded speeches of patients in the dataset can help us identify whether or not the patient has Parkinson's disease or not, whether they are positive, either they are a case of Parkinson's, or whether they are not a case of Parkinson's disease. In order to do this, instead of using the Google Collaboratory network which we used before, we're going to use Anaconda, which we can actually download online. So after downloading Anaconda, so there's Anaconda, and basically it is a data science platform. So what is Anaconda? Anaconda is basically an innovative data science platform which basically can run various types of apps onto it, or launch various types of apps onto it. After downloading Anaconda, you should get a green button like this, and we can access the environment, the Anaconda Navigator. And here we have all the applications which are installed. So Jupyter notebooks, after being downloaded, will be installed onto the Anaconda, and it basically can be launched from here, from this interface, from this user interface basically. So we're going to launch Jupyter notebooks, where we're going to basically code our data, and we're going to access, okay, our file, so untitled folder, and in this case we have the Parkinson's dataset that we'll be using over here. Currently it's untitled, however we're going to give it a new title. So entering or clicking on the untitled, we can now give it a title. So the first thing we're going to do here before processing our dataset is basically import various libraries. These libraries are going to basically help us, okay, work with our dataset and also create the visualizations and the outputs we need from our dataset. So one of the first libraries here we're going to import is basically warnings. Warnings.filter warnings is going to help us prevent getting various useless warnings pop up from our code. So basically we're coding, we have an old library, like an old version of sklearn, okay, and we don't want extra information from that code to basically pop up during our coding. So this is quite important to help us ignore excessive warnings within the code itself. The next, we're going to import NumPy as NP, which is going to help us with the computations. We're going to import pandas as PD, which is going to help us basically create our data frames. And we're going to import the OS and the SYS. We're going to import Lux, which is going to help us basically with the conversion of attributes towards the visualizations. And we're also going to import sklearn.preprocessing, from which we're going to import the max scaler. We're going to also import XGBoost. And XGBoost basically is an open source software library which helps provide a gradient boosting algorithm. It's a type of ensemble learning algorithm which basically uses models to train the data, producing superior outputs. We're also going to, from sklearn model selection, import the train test split, which is going to help us train and test our data to a training dataset and a non-training dataset. And we're also going to import the accuracy score. The accuracy score, of course, is going to give us basically how accurate a particular model we are using is. The next step is basically loading our data set. So we're going to start off by loading the data. The data we have already downloaded, and basically we're going to upload it using pd.read CSV file from which we're going to import the data set. It should have taken it. Now, after that, we're going to try to identify the main head of the data. So how the data is divided into columns, all right, what the columns are made of, okay, and what type of data the columns contain. Each column, of course, contains various rows, and within the rows we have a variety of data inputs. So we're going to have a head of 10, and we're going to see what prints out. So over here, basically, the data set is going to give us basically the name of the patient, which is basically, in this case, an ID or a patient ID. Here we're going to have the hertz, okay? So we have the hertz, which is basically the speaking attributes, okay? Related to whether a patient is Parkinson's positive or not. And then we're going to have the status, okay? So the status is telling us basically that the patient here, for example, is a case of Parkinson's, which is 1, or is not a case of Parkinson's, which is going to be classified as 0. So the status is basically our classification of whether a patient is Parkinson positive or negative. We can define the shape of the model. With the shape of the model, we can know how many rows and columns it has. So basically our data set is consisting of 195 entities. So we have 195 entities over here and 24 columns. So in these 24 columns, we're going to have around 195 patient entities, each of which having particular data. The next thing we want to see is whether there is any null data in our data set. We're going to do df dot is null dot number, and it's a function, so this should be sum. Okay, so after rearranging our code here, it was not num but sum, okay? We can also see that we can toggle between pandas and lux. So it gives us a function of toggling the data into visual form. Okay, so if we do panda or lux, we can get an output possibly which is visual. This case is not coming because we have no data. Most of our rows and columns do not contain any form of null data. All the data is inputted and all the data is basically present where it has to be. Now there is df types. So with this, we're going to see what types of data we have, data types. And basically most of our data is going to be a float. We have mostly floats, and we have status, which is an integer. Integer because it is either 1 or 0. Next up, what we're going to do is we want to check whether there are any label imbalances. And we can do that by also plotting a data frame and also by doing basically a display plot. Okay, so we can create this by doing a pair plot. So how can we actually see whether there is any label imbalance in our data? So first off, we're going to write the title check for label imbalances, and we're going to import matplotlib.pyplot as plt. We're going to import seaborn, import as SNS. Next up, we're going to do temp equals df. So we're going to do the status, and we're going to do the value counts. Value counts, which is a function. We're going to do temp df equals pd dot data frame, inside of which we're going to have the status, which is going to contain the temporary index. We're going to have the values, which is going to contain the temporary print. And the temporary print is going to basically contain the SNS, the seaborn bar plot, which is going to contain the X status, and the Y, which is values. So the Y will be values, so basically we're going to have the data frame, which is going to contain status and temp index values, temp values, and we're going to have the print seaborn, the bar plot. Basically X is going to contain status, Y values, and we're going to have a data temporary df. Now if we click OK, run, it should run. Yes, and this is going to give us basically a bar plot. The bar plot is showing us basically, as we said before, the status. Okay, so the status in our data set basically is telling us whether a patient, in this case, has Parkinson's or whether a patient does not have Parkinson's disease. Parkinson's disease is going to be classified positively if the patient has Parkinson's, and is going to be classified with a 1, an integer. Okay, and if the patient is going to be a non-Parkinson's patient, the patient is going to be given a 0 in our dataset, therefore showing that the patient has got a negative test and therefore is not diagnosed with Parkinson's. This one basically is a visual representation of the variance imbalances in the labels we have in our dataset. And it's clearly shown by this bar plot. It's an easy form of graphical representation. So the next step basically, after identifying the imbalances in the label of the data and also showing whether how many patients with Parkinson's have the disease and those who don't have the disease, we want to see a relationship or a visualization of PairPlots. And this can be done by SNS, which is seaborn, and PairPlot. Okay, in which we're going to do our defined columns. So basically after running this function over here, sns.pairplot.df, we can see that we get a output of basically pairplots. However, when you have a lot of data, the data can be really confusing. It looks like an accumulation of random data points. What we can find here is the status column, and in the status column we can see that we have a particular type of data, which is linear. Okay. Other data seems to be either scattered, it can be random or not. However, it's not that clear. In order to make the data a bit clearer, to see that when we are basically dealing with the data we're working with has a particular type of distribution, we can run a distribution of data in order to see whether our data plots are normally distributed, skewed, or unskewed. Okay, this is important when running basically data because you want to see whether your distribution is normal or not normal. In order to do this, we can basically define the dist plots and our columns, in which we're going to have the SNS, which is seaborn, and the next we're going to say for I in list, we're going to have the df dot columns, and is going to contain the this plot. So basically this is not an I but a 1, that's a mistake. And if we run this, it should now print us our data. Okay, so this plots I, and let's run it. So basically after loading the data, okay, the data was passed and we have an output of graphs, okay. So over here we can see that there are various graphs, okay, being printed out. And each of these graphs, we can see that there is a distribution. This is basically known as a Poisson distribution or a binomial distribution, all right? And we have a normal type of distribution. It is skewed, all right? So it is skewed towards the 0 mark. And if we have, for example, the volume and the density, they tend to be a bit skewed towards the lower data points. So most of the patients over here are getting low scores. So basically now the next thing we're going to do here on our dataset is identifying outliers. Why is it important to identify an outlier? Most of the data, if we have outlier data in our dataset, is going to skew our data towards that data point or towards that particular outlier, and therefore the data we might be interpreting might be totally wrong. In order to identify a particular outlier, or where there we have any outliers in our dataset, we can do this by running a basic simple test known as a box plot. The box plot basically is going to show us whether there is any data point outside of the normal data variation and any data outside of the norm or outside of our normality for data is going to be classified as an outlier point. And this, of course, is going to affect our overall data and our overall strength of the data we're using in basically identifying the diagnosis of Parkinson's or not. In order to find whether there's an outlier or not in our dataset, we have to run basically a box plot. And we can do this by doing df boxplots, identifying the columns. So after identifying the columns, we can run SNS Seaborn boxplot, and we define column as we did before, plt.show for I in list. We're going to define select the data types, and exclude any object. From the object we want the columns, and we want the first column onwards, not from 0. And we're going to contain in it the box plot. Now, if we run it, it should work. So here, after running the box plots, where we're basically using the SNS box plot and plotting, okay, the data, we can see that there is an output. So for I in a list of the data types, okay, we're basically plotting the box plots over here. And as we can see, every single plot has outlier data. So every single plot we have has actually outlier data. And what a box plot does basically is showing you the median, the mean, the maximum and the minimum values. So we have the median and mean, the maximum and the minimum values. And we have some outlier data. Now, what we have seen in the brief of our data is that although these outlier data points might be seen as outliers, in reality these are acceptable data points, and therefore they can be included within our data set, okay? Because they fit in the classification or the definition of the data collection that we are carrying out with regards to the data set we're using here. So basically, after looking at the box plots which we have seen over here and at the data and the outliers, now the next thing we're going to see is whether our data is correlated or not to other data in our data set. What is the problem with having highly correlated data? Highly correlated data, the problem with this is that it might give us a false reading. It might give us, for example, a false positive or a false negative, because if you might have highly correlated data that you don't want to be highly correlated, it's of course going to basically trigger a false level of interpretation within the data set. So in order for us to see whether or not our data is highly correlated or non-highly correlated, whether it is positively correlated and negatively correlated to each other in a very strong manner, we can basically create a heat map. And the heat map can be created by the Seaborn library we have basically imported beforehand. So we start by writing the title, correlation heat map. And we're going to basically plot PLT, the figure, in this case the heat map, which is going to have a size of figure 10 by 10. We're going to have the Pearson correlation, which is basically the core, equivalent to df.correlation, the function basically of correlation. And inside of the heat map, the SNS from Seaborn and heat map, we're going to include the Pearson correlation, the annotation, which is going to be labeled as true. So this should be fixed size, and now it should run. Let's see. Okay, yes, it runs. Okay. So over here, what we have is basically a heat map. On the right-hand side of the heat map, we have basically a color gradient. This means it's basically highly positively correlated, as it is light. Okay. And the darker it is, it's less correlated, highly negatively correlated data. So for example, if we look at HNR over here, okay, and we look at HNR, these are highly correlated in a positive way. So it's given a correlation coefficient of 1. And if we look at the data here, the data is becoming lighter, okay? There's a light band of correlation. Most of the times, these light bands of correlations are because they're correlating to themselves. If we look at the status and we follow the status, most of the status readings are not correlated well to each other. And that's a good thing, because we don't want to have something correlating to our diagnostic outcome very strongly, because if it's very strongly correlated, most of the times the data is false, okay? It's not going to be something that we want to have in our data set. If we can see over here, for example, there is some strong correlation between the hertz, the voice hertz we have over here, the readings, and the status. So there is a correlation between the pitch of the patient, how he is speaking, okay, and his diagnosis, whether or not he is Parkinson's or not. So this makes sense. However, it's not very strongly correlated. It's in the range of 25, somewhere here. So that's okay. However, if we look at these correlations like PEPE or HNR, they seem to be very strongly negatively correlated to each other. When we have data which is strongly correlated, preferably we try to eliminate it from our data set, because otherwise, like anything in data science, everything is going to be skewed towards the strongest correlation, and it might basically divert our observations from the actual diagnostic criteria, what we want to actually obtain from our data set. So now the next step, after basically seeing our data in the form of a heat map, we're going to try and separate our dependent and independent variables from each other. How are we going to do this? Basically, we're going to select the X and the Y. The X will contain our independent variables, and the Y is going to be our dependent variable, which in this case is our diagnosis. It is basically the status of the patient, whether they're Parkinson's positive or negative. Okay? So in order to do this, we're going to separate the dependent and independent variables from each other. And we're going to do this by basically creating the X, which is going to contain our independent variables. And we're going to drop basically the status bar, because the status bar is basically our dependent variable and we don't want it to be part of the independent variables. So the status bar over here is basically our dependent variable. And the name basically does not contain any data, it contains non-integer data. So it's basically a string and it's technically useless, okay? And we're going to also add our axis, which is equal to 1. In the next column, we're going to create our y, which contains the df, the definition, and we're going to contain the status, which is what we want. Okay, it is our dependent variable and we actually want that. So this should drop basically these two columns over here. So we want to drop these two from our independent list of variables because we don't want them to be part of our X data, and we want to include in the Y the status. All right, this should run actually, and yes, it takes it. So now we know what is our dependent and independent variables. Next, what we're going to do is detect a label imbalance. So detection of label imbalance and correcting the label imbalance. Why are we going to correct the label imbalance? As we saw before over here at the top, over here we have a label imbalance. So basically there are more positive cases than we have negative cases, of course. However, when it comes to feeding this data into an algorithm like regression, like k-means, like for example random forests, this data imbalance can give us problems when it comes to processing the data further down inside of a correlation matrix, or for example inside of a classifier basically. So what we need to do is, before throwing the data and analyzing the data, we want to make sure that our data is falsely balanced. It becomes balanced in both ways so that we can actually have an equal comparison or a fair fight between the two variables. Okay? Otherwise, we'll create a lot of skewness in our data towards one area. So how can we do this? We can do this by, from imbalance learn, from IMB learn, basically imbalance learn, we can oversample, which is basically going to overinflate the data that is missing. We're going to import random oversampler, and it does what it says it should do. It's going to randomly oversample our data. Next, we can actually just copy this. All right, to make it faster. Next, we have oversampling. It becomes undersampling. Import random undersampler, and from correlations you're going to import the counter. So, and then we're going to print our counter. So print function and counter, which we want to print is the y. Okay, basically from the dependent data that we want. And basically it's going to give us how many ones and zeros are present in our data set. So if we run it, it should give us our data. So it's not working, and this should be a capital because it's counter, and this should also be a capital. In order to run imblearn over sampler and under sampler, we need to import the module. So basically import imblearn, and this should actually run. So over here we can actually see the output. So over here we can actually see the output. What we have here is that a counter here shows us that, for example, for the ones, which is the true positive case of Parkinson, we have around 147, and for zeros, the non-Parkinson diagnosed cases, we have 48. Now, when we're sampling our data and we're basically trying to balance out these counters, we actually try to go for the oversampler because we don't want to lose important data. This is important data for sure because, of course, if it's a positive case of Parkinson's, it's 100% important data. So what we're going to do is we're going to create ROS, a function known as ROS, which is basically a random oversampler. Random oversampler. And it's going to be a function. And basically the ROS is going to give us the X random oversampling, the X ROS, and the Y ROS, which is equal to ROS.fit resample of X and Y. And then we have print the counter, again with a capital, which is we want to print is the dependent variable, so the Y ROS. If we run it, it should actually print. Hopefully, yes, it does. Okay, so the counter over here changed from 147 and 48. It's now giving us 147 and 1147, showing us that our data now is actually well balanced. Okay, so that's what we want. So basically, after doing random oversampling, what we're going to do is basically scale our data. Why is scaling important? Scaling of the data is important because what we want to do is transform all the features of a data set so that they all fit the same scale. And when we feed them eventually into, for example, logistic regression or a k-means or random forest, etc., etc., we basically are improving the optimization. So these learning algorithms, like gradient descent based optimization algorithms, tend to be sensitive towards the scaling features of the input. So our input data that goes into the gradient descent, for example, optimization algorithms, example, logistic regression, all right? They tend to be sensitive towards the scaling of the features, okay? So in order for us to scale our data, we have to use the min-max scaler, which is going to help us select a range of data from -1 to 1, the interval of the data. So scaler is going to be the min-max scaler, which is going to give us a reading between -1 and 1. This is going to be called our interval of the data. Here we have the X equals scalar dot fit transform and we're going to have the Y equals the Y ROS. This should scale our data and actually it should be okay, it should be received. The next step in analyzing our data basically is going to be feature selection. What is feature selection? Basically, feature selection is identifying those features in our dataset and not retaining the extra features which are basically taking up a lot of space. In order to do this, we're going to use a type of feature selection, all right, or dimensionality reduction technique known as principal component analysis or PCA. So what on earth is PCA? Basically, principal component analysis, if we look at Wikipedia, is a technique for analyzing large data sets containing a high number of dimensions or features per an observation. For example, in our Parkinson's case, we have a lot of observations related to Parkinson's. For example, in our case, it is the voice or the hertz of the voice. Formally, PCA is a statistical technique for reducing the dimensionality of the data set. What it tends to do, basically, in summary, is that it gets our large data set and basically reduces its dimensionality. Okay, it makes it smaller and therefore more easy to compute. How on earth are we going to do this? We're going to do this by basically running some code. So basically from sklearn dot decomposition, we import PCA. The PCA is going to be equivalent to PCA with 95 retention of variance. So in our data set, we would like to retain 95% of all our data set. X PCA is going to be equal to, so the independent variables are going to be equal to the PCA.fit transform, and we're going to transform the X. After transforming the X, we want to print the values, so we print the X.shape, which is the original data, and we also print the XPCA.shape, so it is the reduced form of the data. Now, if we run the code over here, I modified my code. This has to be capitals, okay, guys? So XPCA should be capitals, okay? And of course, we print XPCA.shape. If we run the code, it should take it. So as we can see here, guys, the results came out here, okay? So this is the original X shape over here, and this is the PCA, okay? So what principal component analysis is doing is reducing our dimensions, and we actually removed quite a lot of data. So from 22, we are now down to 8, and that's quite a big loss of data. However, this data is not actually lost. What we're doing is we are retaining 95% of the features which we need to use in interpretation, and we are using less of the noise data, the data that we don't actually need in calculation. So the next step after reducing the dimensionality is basically creating our training and our testing set of data. So what we're going to do next is basically create our training and testing set of data. We're going to do this by basically putting in some code. So X train and X test. We have the Y train and Y test equals train test split. So we're going to split our data into 20% training and 80% test data. So we have the X PCA data we saw before, the principal component analysis, we have the Y, the dependent variable, the test size that we want 20%. Of course, we can change this to like 30% or 10%. However, 20% is usually a standard. And we have the random state. In this case, we're going to apply 7 to it. And it should run. Yes. So this basically what it did is it split our data into 20% training data and also testing data. So why is this important? Basically, when you have supervised learning is a type of machine learning which involves labeling data and also having a training set of data and also a testing set of data. So in machine learning techniques, which are supervised, you actually are basically giving a sample to your overall algorithms or classifiers. So 80% of the data is retained for testing. Okay, so we can actually write it down here. We retain 80% of the original data is kept for testing on. Okay, and we can actually run it again just to make sure. Yes, it took it. Now what we're going to do next is basically identify various algorithms. Okay, so As we have seen before in another video, there are various algorithms and classifiers we can use. There's logistic regression, there is k-means testing, there is random forests, etc., etc. In this case, I am going to use more machine learning classifiers and algorithms. And out of all these algorithms, at the end, we're going to see which one of these algorithms has the best outcome, which is the most accurate. In order to do this, we need to import some libraries. And we're going to import from sklearn metrics. We're going to import various libraries, basically confusion matrix, accuracy score, the F1 score, the precision score, and recall. So those basically are going to be imported in our system. We can actually just import them right now. And we can, for example, start importing lists. So list. So this should run, and yes, it is taken. So we have also created the lists, which we're going to use eventually in our algorithms. Now, basically, the next phase here, we're going to apply all the algorithm. The first algorithm we're going to start off with is logistic regression, which eventually we're going to compare to other algorithms are going to be compared to. So it's a type of classifier as we've seen before. So from sklearn dot linear models, we're going to import logistic regression. The classifier is going to be equal to logistic regression, and is going to be equal to some data. So basically, it's going to be equal to this. The classifier is going to be equal to logistic regression, etc. like linear. Next, we're going to place our logistic regression, which is going to be equal to the classifier. Of course, is going to check for best fit, and the best fit is going to contain our data, xtrain, the training data, and the y. These are the training sets. And the y prediction, the output of the dependent variable, is going to be equal to classifier dot predict. Of course, we have the x testing. So this is going to be small, x test. The next phase is going to be the accuracy. Overall accuracy is going to be given by of the logistic regression accuracy score, y-test, and y-predict. The next classifier we're going to use is basically a decision tree. So a decision tree, basically we're going to do the same thing. From sklearn.tree, we're going to import the decision tree classifier. And again, the code, similarly, we're going to eventually type in a code related to the decision tree. So the classifier equals decision tree classifier, as we did here. So classifier equals logistic regression. And in this case, we have a random state because it's a random decision tree. The decision tree equals classifier fit, xtrain, and ytrain. And then we have the prediction. So prediction is going to be equal to the x-test, the testing data. And accuracy is going to be given by accuracy score. So another classifier we can use to check our data is also a random forest. As we have seen before, random forests tend to be more accurate compared to other types of classifiers and algorithms like logistic regression. So from sklearn ensemble, we're going to import the random forest classifier, and the same, we're going to basically apply some code. In this case, we have a classifier tree, because it is our third classifier. The random forest classifier equals the random state, 14. Random forest equals classifier tree and fit, which we have the training data, X train, Y train. Prediction equals classifier, predict, X test. And we have the accuracy score again. Now to make it shorter and quicker, basically I'm just going to paste in some code for the other classifiers, the remainder of the classifiers, which we're going to have basically an SVM, a Poisson Neve base, and a Bernoulli Neve base. So we have the SVM here, which is a vector machine. From the sklearn SVM, we import the SVC, and the model, which is SVM, equals SVC cache size. The SVM model equals SVM fit, the training, the prediction, and the accuracy score. Here we have a KNN, which is basically K nearest neighbors. From sklearn neighbors, we import KN or K neighbors classifier, and the model is a KNN3, and the classifier basically has neighbors, which is equal to 3, the 3 nearest neighbors. The fit will contain, of course, the training data. We have the prediction data, which contains the predictor, the dependent variable, the X test, and the accuracy SVM, okay, which has an accuracy score of Y test and prediction kernel of KNN3. The next we have the applied Poisson-Neves bias, okay. From sklearn we also import the Neves bias here, and so on and so forth, okay. So these are all basically classifiers, which are going to be used to predict the accuracy of our testing or of our data. Now, basically what I did here is basically combining all of the above. So what am I doing here? All the voting classifiers above, okay, including the linear regression, okay, random forests, the Bernoulli, the KNNs, the SVMs are all basically inserted into one particular voting classifier over here, which is known as the EVC. The model of EVC gives us a fit for the training set and the prediction, the X test, and the accuracy score. Here we have lists. So we have the first list containing logistic regression, decision tree, random forest, etc., etc. The secondary list contains the accuracy scores, and the third list contains the classifiers. What we're going to do next is we're going to print out all of these together to see which of the classifiers is the most accurate. Instead of looking at each one individually, which will take a lot of time, we can basically do this in a simple way by basically plotting a graph. And the graph will give us a clear output of which one is the best and most accurate algorithm to be used when we're basically working with our data. If we run the data, it should print us our accuracy scores. And actually, we do have a printout over here. So what we have over here is the method used. In this case, we're using linear regression, random forest entropy, SVM, KNNs, okay, Bernoulli, GBN, and the voting classifier. So out of all these, which one is the most accurate? As we can see over here, the most accurate of all these is the KNNs, okay? And second most accurate is going to be, as we said before, the random forests, okay? The random forest classifier, the decision trees, and the third most accurate is basically going to be the Bernoulli and the Poisson Neves bias. We can see the accuracy score versus the type of method used in this graph. This is an easy visual representation of the data, and we can see that the most accurate type of score, the most accurate classifier we have in our data analysis is basically the KNNs. So the next part, after seeing which of the models is the most accurate, we're going to basically use XGBoost. What is XGBoost? XGBoost is basically a library that is going to boost our data. So basically, XGBoost is going to classify extreme gradient boosting using gradient boosting algorithms for modern data science problems. It falls under a category of ensemble learning, as we said before, in machine learning. It's going to make our data output more superior. So makes our data output more superior. It sort of boosts our data. In order to carry out XGBoost, we're going to basically copy this very basic simple code. We have a model which is XGBoosted, XGBoost classifier. It's a function. and basically the fit. The fit is going to contain our training data. And if we run it, it should boost our training data, okay? And this basically is the boosted data, right? So all the independent variables that can be seen here, which eventually were feature selected, have now been boosted. So the output basically boosted all of the data here. Next up is we want to see which of these models is the most accurate and how much accuracy we have in our data itself by using a confusion matrix. So what a confusion matrix does is basically telling us which of the data is containing any actual positive or false positive, or actual negative and false negative. So after boosting our data over here, now we're going to see how much of the data predicted is actually accurate. So the predicted data accuracy. We can do this by running some simple code, calculation of accuracy, which is basically the Y prediction. So the Y prediction, which is the dependent variable, as we said before, is going to use an XGBoosted model for prediction. With the accuracy score times 100, we will see how much of the predicted data is actually accurate. From the output, we can see that the predicted accuracy or accuracy score is around 93%, which is not bad. 93%, as we saw before, comes close to the most accurate version of model we are using. The most accurate classifier we have over here are these basically, and these, the most accurate classifiers are giving us effectively also a high level of accuracy. So the models we chose, like the SVM, for example, or the decision tree, gives us a high level of accuracy. The next step after checking accuracy is basically running a confusion matrix. And why should we run a confusion matrix? A confusion matrix, as we saw in a previous video, was basically the difference between having a false diagnosis, an actual diagnosis, or having a false positive diagnosis and a false negative diagnosis. This is important because when we create a diagnosis, when diagnosing a health condition, okay, we want to know that the patient is actually sick. Okay, you don't want to diagnose a person telling him, okay, you have Parkinson's disease, when actually he does not have Parkinson's disease. So how much of our data in our data set is actually Parkinson's or true Parkinson's, and how much data is actually false? So from a scalar matrix, we're going to import confusion matrix, and the confusion matrix is going to contain the Y test, all right, the tested models, and the prediction model, the X test. And we should get a confusion matrix, how much of the data is actually true or false. The next thing we're going to also add is basically the F1 score, okay? So what on earth is an F1 score? The statistical meaning or significance of an F1 score in the statistical analysis of binary classification. F scoring is a measure of testing accuracy of data. It is basically calculated from precision and recall of the test, where the precision is the number of true positives divided by the number of all positives, including those not identified correctly. The F1 score is a harmonic mean of precision and recall. So, the F1 score is a value between 0 and 1. A higher F1 score indicates better performance. So, the greater our F1 score, the greater is our performance. So, from a scalar matrix, we're going to import other libraries like the ROC curve, the AUC, area under the curve, confusion matrix, etc. We're going to print the classification report, okay? And we're going to print the confusion matrix, okay, which is going to contain our confusion matrix, which is here. And this should give us a confusion matrix for our model. If we see the output here, we can see that there's the precision of the model. The precision of the model is 1. That is really good. We have a precision of around 90% and an F1 score close to 1, which is around 0.91, all right, 0.95. Our confusion matrix is showing us, okay, that we have around. So our confusion matrix over here is actually showing us that we have around 4 which are actually false positives and 0 which are false negatives. So out of all the positives, true positives, we have 4 which are falsely positive. Okay? These are patients which were classified as Parkinson's, however, they don't really have Parkinson's disease. And this basically shows us around 0, which are false negatives, or patients which were diagnosed as not having Parkinson's, but in reality having Parkinson's, and in reality there are 0 patients. Now, to look at other precision scores for other models or other classifiers, we want to run a confusion matrix on a list. So for I in list, we're going to print the classification report and the prediction. We're going to print the confusion matrix for the various classifiers. And we can run it. And here we can see that we have the precision reports, we have the confusion matrices also for the logistic regression, for the decision tree, for the random forest classifier, the SVC, okay, and the K-neighbor classifier. For each one of these, it still shows that each one of them has around false positives of around 4. Okay? If we look again at our confusion matrices, most of the false positives are 4. Okay? Precision of the models, again, is variable. So the precision and the F1 scores here are low for logistic regression. Decision trees are a bit higher. It's greater precision. However, F1 score is 0.91. SVC has a precision of 0.92 and the F1 score of 0.92. It shows to be a bit more balanced, possibly. And K-neighbors has a balance of 96. As we saw before, K-neighbors was the most accurate model. Okay, so the F1 score is also the most accurate here at around 0.96, therefore showing that the precision and recall here is mostly balanced. Now, in order for us to further evaluate our model, our classification models that we have used before, we're going to carry out an ROC. What is an ROC? An ROC is basically a receiver operating characteristic. It is technically a plot of the true positive rates versus the false positive rates. Therefore, if our curve curves more towards 1 and above the line or the intercept, then we can confirm that the data is actually moving towards the true positive rates rather than the false positive rates. This gives us a greater visual accuracy of our classification model. And how are we going to do the ROC? Technically, in order to run an ROC, we need to code. So basically, we're going to import some libraries. We're going to import the ROC curve, which is important for the ROC. We're going to import the AUC, area under the curve, the confusion matrix, and the accuracy score. Next, we're going to copy some code and paste it. And basically what we're saying over here is defining the plot ROC, which is basically going to contain the model, the X test and the Y test, probabilities of the model prediction, the predictions, the probabilities, the threshold, which is equal to the ROC curve, and the ROC equals the AUC for the false positive rate and the true positive rate. Of course, we want also to include some labels in our plots, so we're going to plot the title, the receiving operating characteristic, plot the false positive rates and the true positive rates, and area under the curve. We're going to plot the X, the Y, and the Y and X labels for the true and the false positives. And of course, we want to see the curves. So we're going to write plt.show, which is a function. If we run this, it should take it, and therefore this is now coded into our system. So what we're going to do next is basically plot the ROC. So we're going to do plot ROC, and we're going to basically insert the model, the XGBoost model, the X test, and the Y test. And this should actually give us outputs. So from the outputs, what we can see here is that we have most of our AUC very close to 1, and that's what we want. Because as we said before, the closer to 1 it is, the area under the curve, which is here. So anything above this red line is known as the area under the curve. And if the area under the curve is positively correlated, it's positive, closer to 1, this is the border of the curve, and 0.98 is very close to 1. So what we're saying is that most of our data for this model we are using is very close to the true positive rate. And that's what we want. If the data or the graph is very close to the red line, that is going to give us something that we don't really want, okay? Because if the data is very close to the red line, what we're saying is that it is close to 0, a neutral diagnosis, and if it is further away from the red line, it's close to the false positive rate. What we're saying in that case, if the AUC was like this, it would mean that our data is falsely positive. It's not really positive, but it is a false positive outcome. So what we can say is that for this model we are using in our project, the result is pretty good. Now, to see the ROC for all other classifiers, we need to print out code, as we did before, for all the particular classifiers and models above. So for I in range list, print the ROC for the list of our models, and we're basically going to print all of our ROCs for every single particular model we did before in our code. If we run it, we will get an output. So our output over here for logistic regression, we have an area under the curve of 0.91, a bit further away from 1. It's not that bad. Here we have 0.92, which is basically the decision trees and the PCA. The ROC for the random forests, it's more accurate, so it's going to give us a 0.98, 0.98, and this is the k nearest neighbors. This is the k nearest neighbors plus PCA, and this has an area under the curve of 98. As we can see, the KNNs were one of the most accurate models predicted for our data. So the graph is further away from the red line and very close to 1. And of course, here are the other models. So basically, technically, this is the final part of the coding we did for our machine learning project on Parkinson's disease. I hope the coding and the project were insightful to help you grab a better understanding of what exactly is machine learning and how we can use machine learning to help us not only diagnose Parkinson's disease, but see whether our diagnosis is a true and actual diagnosis of Parkinson's disease and whether the model used in the diagnosis is actually accurate or not. So this is basically some basic machine learning where doctors or people interested in applying machine learning techniques towards the science, towards medicine, can use machine learning to help bolster our diagnosis and also medical understanding of a particular disease. I hope it was interesting, guys. Thanks for watching and see you in the next video.